Hello, good morning, good evening, and good night. I am Darius from Binus Aso, and my student number is 290-266-5654. And today we're going to present how to calculate for uh, bending stress, maximum bending stress, and uh, yeah, let's get into it. First off, I will have to uh, give my regards to my instructor, which is Alfan Sarafudin. Mr. Sarafudin has taught me for about a year now in class LA71, and I'm sincerely grateful for that. He has taught me many things in this class. Okay, let's get to it. We go through these questions. Let's go. Okay, I am an engineer. We need to study a cantilever rod with a rectangular beam cross-section 60 millimeters wide, 30 millimeters high, with a length of 1000 millimeters. If the rod's own weight can be neglected and the cantilever rod receives a force directly at its end of 40 newtons, determine. Okay, draw a free body diagram. That doesn't really follow well. But let me go on. So we know that it is 60 millimeters uh, wide, 30 millimeters high, 1000 millimeters long, with a force of 40 newtons. So we draw the body diagram here. 40 newtons, 30 millimeters, 60 millimeters. Yeah, you get it. And then second question, which is inertia. Place inertia of the cantilever rod. And to do that, we use a rectangular formula for inertia, which is 1 per 12 times width times height raised to the power of 3. And after that, we get 135,000 millimeters raised to the power of 4. To find this moment, it's simply just the length and the force. So we get 40,000 Newton millimeters, and for C, we just get the middle of this thing. So it's 30 divided by 2, just 50 millimeters, and I'm pretty sure that was the third question. Yeah, that was the third question, yes. Yeah, find the normal stress. We do these to find the normal stress. And to do that, we use this formula, which is uh, the moment times the C. I'm not sure what that is exactly. Forgot what it's called. Divided by the moment of inertia, and I get 4.44 megapascals. And after this, I'm pretty sure, yes, we need to calculate the volume resistance stress by designing it ourselves. Well, I've already done it before, but I guess I'll just have to make a new one again. Okay, let's start. $60 by 30. And then we finish this, we extrude this by 1000 millimeters. I do it in this direction, specifically just I don't have to bother uh, messing with the later step. So that is done. We go to aluminum because, well, it's A, B, C, D. This is an example. You can use any material you want. And then we start the analysis. Create a study. Press OK. Make this fixed end over here at one end. Make sure it's opposite to the 0 point, guys. So we can do it like this. Remote force right here, smack dab in the middle, right there. Goes 0, 0, 0. You don't have to mess around with anything. And then actually go 40 newtons. And then we simulate this. Start report. We can see it already, it's like 4.311. But this changes every single time because it is very, very computery shenanigans going on over here. It's very precise. Not precise enough because it keeps changing every single time because I'm not too sure. Computers can print things differently every single time. 4.31138. But in my case, I have done this before, so it is different. It could definitely be higher or lower than before, but I got 0.04% before, so this time it could be at least 5-10% ish. And after this, we have to calculate for safety factor, if I'm not wrong. Yes. What is the safety factor if the material used has a yield stress of 6.3 megapascals, maximum stress of 8 megapascals, and a fracture stress of 7 megapascals? We've kind of just ignore these because we don't really need these. What we need is yield stress. Why? Because when you get to these, it's just a bit too late. It's too late. So you want this stress instead. So safety factor is equals to the yield divided by max stress. So that we calculated before. This is the structural stress. Okay, different than this one. Different than the structure, the material stress, the material maximum stress of 8 megapascals. No, we use 6.3 divided by 4.44, and we get 1.42. 4.44 is from the theoretical ones, by the way, guys. And then it says here, if the safety factor of the material is expected to be 1.5, is the structure of the material safe to use? Okay. As long as a structure is above 1, it is considered safe by engineers. But it can differ because the type of materials really matter. So, if you get aluminum, you want at least 1.5 and higher. And for others, like wood, nylon, plastic, it can also be way higher. So, yeah, do keep that in mind, guys. You do keep the material you're using in mind. And then this question. With the same type of weight, length of material, create a cantilever bar cross-section design with stronger safety factor. The answer to this question is in the... Okay. So, I have created this thing here. I had designed this prior. So we have the outer weight, the outer height, outer width, inner width. This just shows the dimensions of this, but yeah. So we use uh, the outer height, outer width, inner height, uh, inner width. So this bar thing is 10 millimeters, and then since we say here it's 30 millimeters, it's because we're using it like this. We're thinking of it like this. So just to make things easier, we think of the outer area minus the inner area. So this is 30 millimeters, but in reality this is 10 millimeters in the middle and 10 millimeters at the top and bottom here too. So yeah, let's head on to the next one, and then we get to prove it with manual calculations. And here it is. Manual calculations. We did this before, so I'll just skip through it. But the only thing different here is this. I use capital letters here and lowercase letters here just to tell the difference apart. So this is the width and height of the outer area, the outer initial inertia, right? Oh, if inertia minus the inner inertia. So after we do that, we plug in the numbers. We get 3.26 million millimeters to the power raised to the power 4. Yes, yes. Ah, and then calculate for the maximum stress with the same formula from before. We just plug in the same MNC because it's still the same from the previous one. Divide that by the new moment of inertia, which is 3.26 million. After that, we get 0.73616. Okay, you get the rest. And then in this section, I just find the safety factor, which is 8.56. After that, pretty sure I need to invent something. I invent, just make the new one. Test it in the actual calculations. Yes, yes. Compare the calculations following of the maximum load stress in the number 7 design with the FEA simulation results of Binus stress. What is the deviation error? Right. I'll have to make a new one again. Start new sketch. Make this rectangles. So 40 times 120. Keep note that this side needs to be taller than the shorter side, right? And 20. Keep that in. 40 millimeters. Oh no, I messed up. That's okay, I mess up, guys. 40 millimeters times 120 millimeters. Oh wait, no, it is wrong. I forgot. It's 100 millimeters. Wait, how can I forget? Oh, there you go. Oopsie. Forty. Maybe going a bit too fast from yourself here. But okay, that's done. Then we just simply extrude it like before. And done. Then we create study. Okay. Just like before, guys. Oh no. Oh no, I messed up. It looks like. Right. Let's pick the same one so we don't confuse ourselves. Make sure it's the same. When we begin stress analysis, create a study. Press OK. Effects. On this end. Okay. Force. 40 newtons. 0, right? Yes. You have to offset this. Since we use that method. We simulate this. We can report. That one was 0.7723 something. So just do this to double check. But it should be around the same. Around the same, not always the same. Okay, let's see here. 0.7722 something, something. Way less than this 0.77291. Definitely gonna be different case for every single time we do this, but you simply just add the form as a stress here, that minus 4. And then question number 10. Based on the calculation in the previous question, synthesize how to design a cantilever beam to perform stronger, be more effective, and still meet engineering requirements. So, like we discussed before, the calculations. The formula for squares, the formula for rectangular areas, it is 1 per 12 times the width times height raised to the power 3. So, yeah, we want as much height as possible, and that increases the moment of inertia, which lowers our max stress. And doing that gives us higher safety factor. I-beams are more cost effective, more stronger, and it's just the simplest way to do it, to make cantilever bars, cantilever beams. Yeah, that's all of it, as fast as I can. Uh, Thank you for listening, and goodbye, guys.